Waves, light waves washing against our eyes, creating a vision of the world around us. Sound waves crashing against our ears, sometimes jarring and other times beautiful. Cosmic waves bathing the universe, all of it explained, illuminated, and connected via mathematics. Sometimes we call it harmonic analysis. Other times we call it spectral analysis. But most people call it Fourier analysis. Of all these sensory experiences, perhaps music more than any other is the one that is most closely associated with mathematics. The Greeks believed that beautiful music was mathematically based music, and that there was a mystical connection between music and mathematics. That music was actually the mathematics of time. Throughout history, music has been at the heart of human culture. Its origins were most likely the patterns, rhythms, and tonalities of nature. Sounds adapted and organized by humans to create melody, harmony, and rhythm. Some of the earliest instruments were as simple as clapping hands. But it was the ancient Greeks who first laid the foundations of our understanding of harmonics, how vibrating strings and columns of air produce overtones which are mathematically related. In fact, the word music itself derives from the Muses, daughters of Zeus and patron goddesses of creative and intellectual endeavors. The Greeks applied the same rigors of rational thought to music as they did to everything else. Pythagoras is said to have made the earliest acoustical observations when he described the arithmetic ratios of the harmonic intervals between notes, ratios which were based on the length of the object creating the sound. For example, octaves, 2:1, fifths, 3:2, and fourths, 4:3. For the Greeks, these arithmetic ratios held great metaphysical significance because they believed that a single set of numbers from 1 to 4 was the source of all harmony. So their theories about music were intricately connected to their mathematical and philosophical description of the universe, how the planets, the sun, and the stars vibrated in harmony, creating a music of the spheres. In the ensuing 2,000 years, we've learned that this connection between math and music, whether mystical or not, is all about waves. Sound is simply a disturbance of air, as Pythagoras observed, a vibration, but as we now understand, a vibration that extends through space in the form of a wave. The initial disturbance can be caused by anything, and that anything is called an oscillator, like a vibrating string. But like ripples on a pond, the sound wave spreads when molecules in the air are disturbed and themselves begin to vibrate. The vibrating air molecules in turn bump into other nearby molecules, causing air pressure to compress and expand. This changing air pressure creates alternating waves that extend from the source of vibration. If a person is in the path of the sound wave, and then the wave enters the ear, it's rapidly processed and recognized by the brain as sound. There are many different kinds of sound waves, but they all begin with a simple sinusoid, like this. This is a perfect A, and this, the S curve, is the sinusoid that represents the sound. Sinusoids are one of the simplest forms of what a mathematician would call a periodic function, which is a function that repeats over and over or cycles through a specific period of time. We use the sinusoid to represent the periodic behavior of sound in its simplest, purest form. It's the most basic wave, moving in a simple harmonic motion with a perfect pattern of peaks and troughs. Sinusoids are largely determined by two basic characteristics: amplitude, how high the wave goes up, and wavelength, which is the distance from trough to trough, or equivalently, frequency, which is the number of waves per unit length. Amplitude and frequency have immediate psychoacoustic correlates as loudness and pitch. As you can see, the greater the disturbance, the greater the amplitude, and the louder the sound. Frequency is simply the number of waves in a given interval. The higher note has a higher frequency than the lower note. So frequency is a measure of pitch, and the geometry of these sinusoids explains why when we play the higher and the lower A together, they sound good together. The sinusoids from each of these two notes fit perfectly inside one another. The higher A is the lower one squashed by 1/2. Of course, not all waves are perfect sinusoids. There are all sorts of waves. Different objects create different types of waves, therefore different types of sound. Strings are the source of some of the most beautiful music on earth. They have so many interesting characteristics. Watch. When we play different strings, we create different sounds, therefore differently shaped sound waves. The same thing happens when you pluck the same string at different positions. Or when you play strings on different instruments. In each case, you create different sounds, therefore different sound waves. And when a variety of sound waves of different amplitudes, frequencies, and shapes are combined, we have music. But the music of the real world is comprised of complicated sound waves, not the simple pure sinusoids we've just discussed. In fact, most sounds are composed of complicated waveforms, whether we're listening to a single instrument or a symphonic orchestra. And while the Greeks may have deconstructed music into simple arithmetic ratios, such as octaves, fourths, and fifths, how can we mathematically understand such complexity? For centuries, we couldn't. Not until the early 1800s, when the eccentric French mathematician Jean-Baptiste Joseph Fourier discovered that waves can be combined and separated. It was a discovery that no one believed at first, but that changed music and math forever. Fourier's revelations didn't begin with music, but rather with his investigation of heat. Friend and advisor to Napoleon, Fourier is said to have become obsessed with heat while accompanying Bonaparte as chief science advisor on the 1798 military expedition to conquer Egypt. Fourier was apparently so impressed by the well-preserved sarcophagi that he kept his rooms uncomfortably hot for visitors, while also wearing a heavy coat himself. The heated problem that Fourier took on in his famous memoir on the propagation of heat in solid objects was the problem of heating and cooling of our Earth, our own cycle of temperatures. The French mathematician developed his understanding of heat flow in terms of Newton's law of cooling, that says that the movement of heat between two bodies is proportional to their temperature difference. Translating this to the infinitesimal scale of temperature differences between infinitely close positions in an object gives the famous differential equation called the heat equation. In Fourier's solution of the heat equation, he found these periodic solutions of sinusoids, mirroring the cycle of temperatures over the year as the accumulation of periodic effects, such as the regular orbit around the sun and the daily spinning of the Earth on its axis. Fourier found that no matter how complicated a wave is, it's the sum of many simple waves. This was an astounding discovery, but for many years, few people believed his theories. After all, how could a complicated wave be reduced to the sum of seemingly many incompatible shapes? Square waves and V-shaped waves have corners, while sinusoids are smooth. But over time, mathematicians affirmed Fourier's discovery and came to refer to the unique set of simple waves that combined to form a more complicated wave as the waves Fourier series. So we're here with Liz Stanhope, professor of mathematics at Lewis and Clark College, and Liz's research expertise lies at the intersection of Fourier analysis and geometry. Hi, Liz.
Hi, Dave.
We're going to talk a little bit about Fourier. And my understanding is that when Fourier introduced this, at that time, I guess, was impossible idea that any function could be represented as a sum of sines and cosines. People didn't really believe it.
Yeah, it seems sort of surprising to do arithmetic with waves. I mean, you're adding and subtracting things that are functions. That seems like a surprising idea to come up with.
And it was even more than that, because it wasn't just, you know, well, you take maybe 3 of these waves, which people maybe could think about because it was like 3 things. But he was actually saying, you know, you could take an infinite number, is that right?
You might even need an infinite number to get at what you're trying to construct.
At that time, I mean, notions of like summing an infinite number of functions was a very complicated thing for people to think about. And the real sort of stopping point for people were what we call questions of convergence. Right? So if you add an infinite number of things, what are the conditions under which that could have a finite limit, something bounded? Let's talk a little bit about, you know, Fourier analysis of a simple function. Fourier is claiming that this thing really is a sum of sines and cosines. So, I mean, how does that work?
So you can decompose it. So you take your squiggly thing, and using Fourier analysis, you can decompose it into its fundamental parts. And its parts will be simple sine waves or cosine waves.
So Fourier analysis is almost like a prism, is a way that I like to explain it sometimes, right? So in the sense that, I mean, you can be given light, passes through Newton's old prism there, and there you see all the components, the sort of pure frequencies of light, right?
You'll take your complicated function, and using this mathematics, pull it apart. So you might have a sine wave with a certain period as one of its fundamental parts, and then maybe a cosine with a slightly tighter frequency on there as another fundamental part, and it'll tell you how much of each of those show up.
Well, what does it mean to add waves and get another wave?
Let's start with two waves, just to make it small. So let's start with one wave that has one oscillation per unit, and let's add it to a wave that has two oscillations per unit. So we can start with those two. And so we have these two waves. How do we add them together? They're not numbers. Seems a little odd.
And I also noticed that one of them is sort of bigger than the other.
So one of them has an amplitude of 3, and the other has an amplitude of 1. So one of them, the bottom one there, is going to oscillate a little bit with less amplitude there.
So there are a number of parameters, actually, that we need to describe any wave. So we're going to be talking about sine waves. So our waves are pinned at one end.
Absolutely, yeah.
And then there's the maximum height they can go to,
Yeah,
which
so
is
that's your amplitude.
Amplitude. And then there's the number of times we sort of fit it into an interval, and that's the
your frequency.
So we've got waves of different frequencies, different amplitudes.
But both signs.
But both
so
signs.
We'll make it easy.
Great.
Yeah, so let's start with they're both pinned, and we'll start adding there because it's the easy part, right?
Great.
So they're both pinned all the way on the left. So how do we add those two waves together there? You just start with that point where they both start, and how high are they away from that axis that they oscillate around?
Right.
They're on it. So
they're on it.
So they're not any height. So they're both 0 value there. So add those zeros together, and that's your first point in the sum.
Okay.
And now cruise along and choose any other point on that axis that they both oscillate around. And then see the height of the first function above that point. Check out the height of the second function.
So those are going to be two numbers, a positive if it's above, negative if it's below, and then I'm just going to add them
together and then plot it above. Yeah.
Right? And so there's the sum of those two waves directly calculated beneath it. And so now we're going to do it at every single point along the curves, right?
And just bring it all the way across.